Thank you for interesting. Okay, hello everyone. Sorry, I'm Durk-Jong Park of KARI, Korea Aerospace Research Institute. I'm very honored to be here to make my presentation about status and planning on space-based solar power R&D in Korea. I will describe KARI space-based solar power roadmap, followed by summary of field tests on wireless power transmission, which KARI did last year. From the lesson learned at field test, several items need to be more improved, which are defined as a work plan in this year. It is KARI space-based solar power roadmap, which is currently updated, not finalized. Step 1 is SBSP validation with a low Earth orbit satellite in 2030. If validation is completely successfully, then in 2040, LEO in SBSP missions for megawatts class to be in operation. In 2050, geostationary orbit satellites to be in operation for gigawatt class. From this slide, I would like to explain about field test on wireless power transmission with KDSA, which KARI did last year, as I mentioned. Regarding the principle of SBSP, it is a very popular principle, so I skipped. But the red box is which KARI did last year. Okay, for the field test, we did two types. One type is ground to air. Second is ground. I would like to explain about some components of the field test. KDSA, the Korea Deep Space Antenna, is working as a space antenna in SBSP principle to transmit the microwave signal to antenna. KDSA was established for KPLO, Korea Pathfinder Lunar Orbiter mission, launched 2022. The key service of the KDSA is S-band up and downlink and X-band downlink, as well as CCADS SL interface with the Mission Operation Center and tracking file generation. KDSA has 35-meter main reflector and 10 kilowatts S-band power amplifier and 20 Kelvin temperature low noise amplifier. Antenna was procured from KARI, Korea Electro Technology Research Institute, for receiving microwave signal. Small patch antenna sized by 100 millimeter by 100 millimeter array. Total 9 patch antenna are comprised in single sub panel, and the total 9 sub panel are comprised in one antenna. Antenna size is 90 centimeter by 90 centimeter for converting microwave signal to DC power. Or rectifier circuit was designed using gallium nitride diodes for quickly visual inspection. The LED is included additionally. Besides KDS and antenna, steering device for changing antenna looking angle, 10-meter aerostat and 55-meter radar truck were prepared for the field test. Prior to field test, mechanical integration test among components were done at KARI astronaut facility, and both electrical integration and EMI/EMC tests were conducted at the KDS site. Regarding field test, near KDSA 2 points were selected as a test site. One is the Yeoju Elementary School with a 1.81 kilometer distance from KDSA, and the other is Yeoju Catholic Welfare House with a 1.82 kilometer. Regarding ground to air, aerostat was staying in the air with a 230 meter height. KDSA was pointing to aerostat and transmitting microwave signal, and the antenna was checking the converted dish power in the field test. The looking angle of the KDSA is 230 degree in azimuth direction and 6.3 degree in elevation direction. Regarding ground test, deployed a 55-meter radar truck were pointing to KDSA. The looking angle of the KDSA is 78 degree in azimuth and 3.87 degree in elevation. This picture shows the LED lamp on the antenna was lighting, meaning that antenna converted each received microwave signal to this power. Video clips were uploaded into YouTube with this address for your interest. Sorry. It is summarized result when KD sent microwave signal with a 2.3 kilowatts to antenna. Antenna can collect 2.4 milliwatts per sub-panel in ground test, and 30.92 milliwatts in ground air test. Power flux density was calculated from dish power of sub-panel with considering the antenna size. Here is summarized what KARI achieved from the field test. Deploying an antenna via an aerostat platform proved to be more budget-friendly and suitable for avoiding obstacles such as a building, mountain, and even village, town. Successful visualization of the power retrieval was achieved by capturing the illumination of the LED lamp. But as a lesson learned, it is required to solve the ambiguity of the near-field radiation gain of the KDSA. On top of that, the steering device with fine positioning accuracy is also necessary to keep antenna pointing to KDSA. Finally, antenna with a higher efficiency is necessary. This is the approach to find the KDSA near-field radiation gain. It is so simple. Some standard antenna gain send the KPL telemeter signal to KDSA, then KDSA calculated its gain from the received signal power, and calculated the allowable power at the antennas based on the calculated near field antenna gain. And fine steering device will be developed with considering the PAT, the pointing acquisition and tracking algorithm. And the antenna with a high efficiency adjust the range of the input power of the rectifier. Actually, the left drawing shows that the input power, the real input power is around 10.03 dBm. It is apart from the expected the input power. The expected input power is the red box. So that is why we get the very low efficiency in the field test last year. So we will change the rectifier diode by using the gallium arsenide, and we adjust the input powers based on the results of the last year. Yeah, that's all. Thank you.